can be.
Function became written in the linear combination of exponential
Okay. It's written there. No. What's the interpretation of this basically? So if f is periodic, okay, then this function f is like some kind of oscillations. So it's kind of some oscillations. So these are also oscillations. So what you are saying is that these oscillations can be approximated, or roughly, can be constructed from these exponential oscillations. Controlled oscillations. Or this oscillation, which looks way different from such oscillations, okay, is a superposition actually. Superposition. It's a superposition of these oscillations actually. So this is what that is.
Sir, इस स्पेस से मतलब कौन सी पर्टिकुलर स्पेस से हमें उठा रहे हैं?
This is what that you have to think of. And in my opinion, we saw something like that actually. So it's the space of continuous function, roughly, which was periodic in nature. Remember?
सही.
So it's functions defined over the interval a to b, okay, such that they are continuous and their values agree on the endpoint of such kind of intervals. Okay, so probably for such kind of functions you can approximate, you can approximate the oscillation of such functions as the superposition of oscillation of these functions which are simple in nature. Okay. Now here is the question. What if f is not periodic actually? You don't have this theory. So this theory kind of breaks down. So when f is not periodic, then you have something which is called Fourier transform. Okay. This is really analog of this, but it's a continuous time version of it. Okay. So my task is not to tell you all details of Fourier transform. I want to see Fourier transform as an operator, and I want to study some of properties of the Fourier transform, relevant to these spaces that we have discussed. So this is my task at the moment. Okay? So when f is not periodic, then we're going to have something that you call it to be Fourier transform. Alright? So for f in L1 of R, so f is a function which is integrable over R. Okay? It's not necessarily continuous, it might be discontinuous. So this function is kind of a crazy space. You don't treat this function as something really simple. It's not a simple in structure. So it could be discontinuous, it could be non-smooth, it could be, but the only thing that we know about this is that yes, we can integrate under this function, under the graph of this function.
Absolutely integrable. Absolutely integrable.
Yeah, absolutely. So that's what we mean actually by integrability of something.
integration is patent.
So for the function f, I'm defining the so-called Fourier transform. As the symbol f of f, calligraphic f is the Fourier transform. Okay. which for the sake of simplicity I'm going to denote by f tilde. Whenever I have this f cap or f tilde, f cap actually at, then I mean the Fourier transform. As, okay. So I want to give this thing as a form of an operator. Okay. So at least this is clear from this that the definition of this the domain of this operator is L1R. Okay. And I'm defining it as what? Operated onto some t. The t is an instant in R equal to the integral of R f of s, the same f multiplied with this function which is e to the minus iota st
ds.
and ds. Okay, s is an R.
That's good.
Where s is an R. Okay? I mean, if you see, you can find analogies between this and the Fourier series roughly. Okay. So if you don't know, okay,
Laplace transform.
you mean by
So Laplace transform is simple or
the Laplace transform, for the Laplace transform, the domain is 0 to infinity.
Yes.
it's 0 to
And you also have a restriction that Laplace transform of the functions can be computed if the function is of exponential order actually. It's of exponential order. While here you don't have a restriction. So f is any L1 function. Unperiodic, it could be anything. That's how you can compute it.
Even discontinuous.
Huh?
Even discontinuous.
Even discontinuous. But
integration.
it's integrable. In other words, this guy makes sense actually. Okay. So now I would like to see that in what space this guy is going into.
Answer range is
So what do you think? What should I do? Let's compute. My claim is that this guy belongs to the space of the continuous function which vanish asymptotically in R. Okay. So in other words, the Fourier transform. Okay. So this Fourier transform is kind of a map
L1R
from L1R
to
okay,
C naught R.
with the one norm into C naught R. And what is the norm on C naught R? Is the energy norm or the infinity norm.
Okay.
Okay, the infinity norm. Okay. So in order to show this well defined, what we need to show? So first thing is that we need to show that this belongs to basically C naught R.
Systems.
Okay. And my claim is that this map is well defined, okay, and it's linear, which is pretty much obvious, and it's bounded. In other words, it's continuous too as well. Okay. And obviously, you need to show this notness of this basically. In other words, as t goes to plus minus infinity, so this function goes to 0 basically. Okay, this function goes to 0. So this is what that we will like to
Sir, operator
show essentially.
operator goes to 0.
Remember,
Function goes to 0.
the function goes to 0 basically. So in other words, the maybe.
What is C naught R?
So the operator, but f of f operated on
Eventually.
t goes to 0.
हाँ सही ठीक सर सेम एज
बाउंड्री शो करना
रेक्टेंगल
जरूरी है,
हाँ?
बाउंड्री शो करना जरूरी, क्योंकि हम जब वेल डिफाइन करेंगे तो दिखा देंगे कि ये सी नोड में है, तो कंटिन्यूस आ
You
जाएगा।
have to show it somewhere. Okay. So the estimation would be enough to show the boundedness. I'm not going to show this. You can read its proof and book, but like I'm going to talk about some of bits, the things that you have here. Okay, so in order to show that this map is well defined, you need to show that this guy is really in this space actually C naught of R. Okay? And in order to show this, what you need to do, you need to compute, okay, the infinity norm of this Fourier transform of f. Okay? This is what that we would like to compute. So in order to compute this, what you need to compute first, you need to compute the absolute of Fourier transform of f. So in other words, and obviously pointwise.
सही
Okay? This is, so this must be equal to what? Integral of r and f of s e to the minus iota st and
ds
ds.
which is less than just yes
And so this is less than or equal to, so the absolute of the integral is less than or equal to
integral of x
r times absolute of f of s, okay, and
e to the
you know, whenever you are applying the result, make sure that you are in the assumptions of that result. Okay, so f of s e to the minus iota st and ds, but this is same as, you know, the absolutes of
सही
these two. So what's the absolute of this guy? Do I need to tell you?
One.
So it's 1 actually. Because we know that e to the minus iota theta, no matter what theta is, equal to cos theta plus iota sin theta. You compute magnitudes, square root of cos square plus sin square, and you get what do you call 1 actually. So hence,
This is fine.
this is equal to r, which is f of s ds, which is same as norm of f into 1. So this is finite. Since this is finite, okay, for all t, okay, so we're gonna say that its supremum is also finite. Okay, so its supremum, when the t is in R, is also finite. Okay, and which shows that what? That is that the energy norm. Okay? So up to this line we have kind of shown.
that is CR
Okay, so,
CR with infinity
so what does this shows actually? Okay? That was too quick. Okay? This shows that the calligraphic f of f hence infinity norm
Minus fine.
can be estimated by norm of f1, which is finite. Okay? And this also shows that this operator is bounded actually.
Okay, first.
Isn't it?
it's
So
non
it's bounded as well. So both things are linearity is pretty much obvious. You can show it from yourself. So in other words, this is a continuous map. Okay? And we can also show easily that it asymptotically goes to 0 as t goes to plus minus.
हाँ लिमिट के अंदर खड़ी हुई t goes to infinity
No, it's not that easy. Okay, it's not that easy. Okay, leaving this as an optional thing. Okay, highly recommend that you should go into this and see that why this goes to 0. But essentially, version of Fourier transform which you are going to see, which are going to modify it soon. Okay, we can see this as a map from L1 into the C0 R, which is continuous and linear bounded, and which goes asymptotically to 0. Now, the whole of quantum mechanics is here actually, L2O4. Okay. So the whole of quantum mechanics is being done in this space, and this is basically a Hilbert space. Okay. Now, one of the fundamental assumptions, so quantum mechanics has many assumptions, but one of the fundamental assumptions is this, that a particle, okay, roughly can be at any location. So what I want is this basically, that this Fourier transform plays a pivotal role. So when I am saying that a particle, roughly in inverted commas, can be at any location, it's not at a specific location actually. This means that a particle, until you observe it actually, so when you observe it, it takes a one particular position. Okay? So when you are not observing it, it's like a wave, it's everywhere actually. Okay? So the position of the particle is like the linear combination of all these positions actually. So you have lots of positions roughly in space, and the position of particle, okay, is like the linear combination of all these positions. Okay. And I can deal such, so it's like, you know, roughly, I mean, if you see, it's something very analog to what we have the Fourier series at. So the oscillations of a function is like the superposition of the exponential oscillations actually. Okay. So similarly, you have, you know, the case here. Okay. That the position of a particle is really the superposition of, you know, all positions where this particle can be. Okay. And this kind of brings in a place for entering the Fourier transform into the quantum mechanics, and it plays a pivotal role there actually. Okay. Now, the current version of the Fourier transform that you have is defined on L1, while all of the quantum mechanics is being done in L2R. So what should I do? So I need to bring in this operator into the L2R, and that's what my next basically what we call objective is. To bring in this operator into L2R. Okay. And L2R is a pretty nice and important space actually. Okay. Many problems, you know, involve the operator whose domain is either L2R or the some subspaces of L2R. Okay. That's valid diagonal functions. So what is the next thing? The next thing is to bring in this operator. So the objective is that I want to turn this operator into an operator whose domain is L2R and the codomain is also L2R. Yeah. So it's an operator on L2R to L2R. So it takes the things from L2R and throws it into the L2R. How I'm going to do it? I'm going to do it in this way. I'm going to do it in this way. So I am writing a theorem, okay, which kind of allows me to get a beautiful conclusion. You can see the proof of this theorem in the appendix of the book, and this appendix is which appendix? That's E.1 actually. So I'm not going to prove it, I'm going to just talk about this simply. Okay. So you can see this in appendix E.1, and this theorem is called Planck. Okay. It's a pretty difficult pronunciation, French pronunciation. Okay. So it's called Planck identity. Okay. So some call it Planck. There's lots of kha in French actually. They say khala. It's everywhere. Kha. Okay. Planck identity, Planck identity. Okay. So what does this Planck identity is telling me? It's telling me something very interesting. It says that if you take f as a function which is continuous with the compact support, okay, in R, with values in R, then this is true. The square integrable of the Fourier transform of the function f, which is from here, okay, over t dt is equal to 2 pi, square root of 2 pi, the square of the function's integral over R. Planck identity tells me that if I have a function which is smooth with a compact support, okay, then the square, okay, so the integral of the square of the function agrees with the integral of the square of the Fourier transform of the function. Okay, this is what that Planck identity is telling me. Now let's interpret this result actually, that okay, what does this result is telling me? Okay. I can say that if f is a space of continuous function with a compact support,
then it is an L1
over R, then is it in L1? Is it in L1? In other words,
or this too.
it's integrable, because this is dense in LB. So this guy is dense in LB, so it's in L1 as well. Then this is representing what? Just think about it. This is representing what? This is the 2 norm of the Fourier transform of f, and its square is equal to, get rid of the square as well, the 2 norm of f. Okay. Are you getting the point? And what does this identity is telling? Think about it.
Radical 2 pi.
Square root
With
2
some
now.
constant. With some constant.
Oh yes.
2 pi
Okay. The square root of
square root of Showing both sides.
No, no. Okay.
Double is for
Okay. Let's keep it this far.
I'm saying
Keep it this far. I can write it like this. Now, what does this theorem is telling me actually? Just think about it and give me the interpretation. What does this is telling me?
it can
So I can say from this
so
result,
if F is in L2 space,
L2, but in CCR. Okay. So this result is telling me that I can interpret the Fourier transform, okay, as a map, okay, from CC of R, okay, in other words, the space of continuous functions with a complex support with the energy norm, okay, into what? Into L2. Okay. L2 of R
and now
with
enough.
the norm. Okay. And so if okay, this is the case, and we can also
I didn't get the free norm. CCR.
no on CCR you have infinity norm. On CCR you have infinity norm. No, sorry, two norm. Should be two norm. It's two norm. CCR. Two norm of L2R. Okay. F can be shown that it is linear. It's bounded. Why bounded? Because of this identity. Instead of inequality, you have an equality here actually. Okay. So it's indeed bounded. Okay. So it's continuous actually. Okay. And so this map is what do you call? It's linear and bounded actually, and satisfies this identity. Okay. Now, so somehow, we kind of set our target space. We kind of got use of this by use of this conventional identity. We got a target space as L2R, but we are still not done with. So we want L2R here as well. Okay. That's in domain as well. So that I can see this as an operator from L2R into that.
So this operator is different from the previous one of L1. This one is.
This operator is same as the previous one.
Definition is same only.
Definition is same. We can somehow show that if you assume F from here, using this definition, you can show, for this you need to see the proof obviously, you're going to have this identity. Okay? And if this identity is true, so see, you're going to have this identity, and if this identity is true, I can interpret the same operator as an operator from CC infinity into L2R, which is linear and bounded. So how can I now take this vector how can I extend this operator over L2R? So do we know any relationship between CC infinity and L2R? So CCR actually, so that's space of continuous functions with the compact support in R and L2R. So we know that this space is dense in L2R. Okay.